Yes? Yes. Oh. Thank you. Yeah. Okay. Okay. And all right, we're business. Great. Thanks for having me. Many people in here have heard me already complain a lot about the technical difficulties that I had, so I will just give a quick mention to my computer was locked yesterday by Space Telescope. I was on the phone with IT for hours. I had to go back and forth between computers. Got resolved 30 minutes ago. So if there are a couple text problems or whatever, hopefully there aren't, but just a warning up front. I am at the Space Telescope Science Institute in the Transient Science Space Telescope group, TSST. It's a good group of multiple faculty members, lots of postdocs, some Hopkins grad students, and for those of you who might be applying, there should be an ad coming out for a new postdoc in the next couple weeks or next week, I think. So, okay, so basically, JWST has been up now for yes.
Sorry, we don't have
Okay. Let me check if it says that it's all on. I can see audio going up and down. So is it on? Oh, it's like the owl.
We heard the echoes earlier.
Oh, we did. Yep.
Yeah.
So are you sure it's that person has their sound on? And stuff?
Can anyone else on Zoom hear? Yes. Okay. Yes.
Okay, everyone else can hear.
Okay,
So it's
so-
just
All right, so JWST has been around now for, this is the third cycle, and that has given finally in the last basically 2 years sufficient baselines to look for transients. So we've been now searching for a lot of time because JWST, although not a survey telescope, you know, as in it is not designed to really repeatedly visit the same patch of sky and look for transients like this and get, you know, repeated observations. It's just very expensive to turn it and do that. Because it's so sensitive and its wavelength range targets very high redshift, we've been finding high redshift supernovae. So basically today I'm going to give a little tour of what we found with JWST and what we're kind of going to leverage that into for the future. So I'm going to talk a little bit about just supernovae in general. I know everyone doesn't do supernovae, although everyone should, you know, just kidding. And actually don't, because then there won't be any jobs. And then I'll kind of go through the first few years of JWST and what we did and what we found. I'm going to go through these discovery highlights, just a few highlights kind of one by one. And I don't have time to go through everything. And then a few of these are going to be strongly gravitationally lensed. So I'm just going to do a few slides on what that means and why we're interested in them, and then show those. And then I'll talk a little bit about the future at the end. And then I actually will be around all week. So if anyone has any questions about anything specific here, happy to chat about it in the next few days. Okay, so some supernova background. I'm going to go through our different supernova types, why we actually care about them. These are important end stage of cellular evolution, so you can learn a lot about progenitor physics, and in particular, as I'm going to say, as a function of redshift. I'm just going to go put these all up at once so we can just kind of see them all at once. So obviously, there's a large portion of supernova science that is cosmology. So there's a whole section of these that are so-called standard candles. And then also tracers of various stellar population, you know, star formation rate properties that we can then trace as a function of redshift, particularly in regions where, you know, individual stellar measurements are just not possible, so particularly at high redshift. So these different supernova population or supernova types that I'm going to go through basically go into two branches. So on the left-hand branch is, I guess, this, yeah. So on the left-hand branch is supernovae that are coming from progenitors of less than, say, 7 solar masses or so. And these are, at the end of their lives, white dwarf stars that then, if they have a companion, which it's up for debate, as you can see in this little figure, whether that companion is another white dwarf or some regular main sequence star or whatever. But the companion causes the white dwarf to explode in what we call Type Ia supernovae, and that is what's used for cosmology, as I'll talk about, of course. And then on the other side is larger progenitor masses. So one's greater than 7 or so solar masses, which end is what we call core collapse supernovae. And further subdividing those, so again, the white dwarfs on the left side and Type Ia supernovae, they form kind of their own subclass, their thermonuclear supernovae. And just because of basically historical reasons, supernovae tend to be classified by their spectra. And so the Type Ias, what we look for are the silicon absorption is kind of the main thing that we look for, which is at about 6,000 angstrom. So what that basically means is it's very difficult to spectroscopically classify Type Ia supernovae at high redshift, as that moves into wavelength regions that we just don't have access to from most resources. So JWST highlight, as you can see. And then the core collapse part is basically I'll say basically two major subtypes. Theoretical electron capture supernova, I'm going to skip that, but Type 2P, the P is for plateau, as these are long-lasting, kind of plateaued supernovae. These are the most common supernova in the universe, and you can see kind of intermediate mass range and come from red supergiants. And then on the extreme side here, Wolf-Rayet stars or similar cause these stripped envelope supernovae. So these are ones, as you can see on the right here, spectroscopically different from Type 2 having hydrogen. Then Type 1b has helium but no hydrogen, and then Type 1c has no helium or hydrogen. So that's how these have been classified over time. There are about 1 million other subclassifications that, of course, I'm not going to go into, but these are the main ones and the ones that I'm specifically, those three, Type 1a, Type 2p, and 1b or 1c, these stripped envelope. Those are the ones I'm going to highlight as having been found by JWST. So, all right, I'll start with the 1a's because everyone's favorite, right, is 1a cosmology. So these Type Ia supernovae are one of our best cosmological probes, or our worst, depending on who you are. And the way that they basically work is these are what we call standard candles. So ideally, every time you measure a Type Ia supernova, you'd be able to put them on a single line like this. That would be the best choice, or best thing you could do. Because then what you'd basically be able to say is, okay, they all belong on this line. And then based on distance, you'd be able to say, okay, well, this one is fainter, and therefore it's further. Just straight, distance measurement in standard candle, not a problem. In fact, they look more like this, where there are two characteristics of 1As that are not just making them standard, they're more standardizable, is these less luminous supernovae fade faster, more luminous fades more slowly, and then it turns out also bluer supernovae are brighter and redder or fainter. So there's these two extra corrections that we do to make these supernovae actually standard. And this one on the right is actually what you get after applying those corrections. So the reason this is important is because each of these components have been calibrated at low redshift, basically. This relationship of brighter is broader, this color relationship of bluer is brighter, and our whole method of doing cosmology is all done historically at relatively low redshift, and is now being extended out to higher redshift. So this has been done originally out to kind of intermediate redshifts of say 1. What's basically done here is just take that distance that you measure. So after all that stuff, this is how bright it is. Shape, this broader brighter, this bluer brighter. You apply all that, and you get a distance, just the y-axis, as a function of redshift. And by comparing different models to that distribution, so now relative to that central model, this is basically what was the initial discovery of dark energy. It's like, yeah, okay, this one seems to work better, and it's the one with dark energy in it. So this was the original use of Type Ia supernovae. Okay, so original use of Type Ia supernovae, and you can see extending to about redshift 1. This is today's diagram. It's log, so it's the exact same thing, distance versus redshift, but now extending, about the same to redshift 1. In fact, it goes to about redshift 2. But you can see we've discovered a whole bunch of these over the last 20 years or so. It's the focus of a lot of surveys, and it's even future ones, such as you've probably heard about upcoming LST, Roman, which I'll talk about. A lot of effort into Type Ia cosmology as a function of redshift, in particular to measure dark energy and see whether it's changing with redshift. I'm going to come back to that, but just keep this in mind. So core collapse supernovae. A lot of people doing 1A cosmology. How about on the core collapse side? So now we're over here on this kind of larger than 8 solar masses, and in particular talk about the 2P and the 1BC. So the with and without hydrogen massive core collapse. So these are valuable because they kind of trace stellar population evolution. And here's a plot. You can ignore some of this, but basically the light blue are discoveries of core collapse supernovae over the last forever, which you can see also extend to about 2. This one here is actually just an upper limit, lower limit. So no discovery there. So this is going to about 2. So both 1As and core collapse going to about redshift 2. Just to bring this back up so you can see this is going to about redshift 2 for 1As. So I'm just going back here. So the core collapse, what this is showing is the cosmic star formation history in blue, and then some theoretical could be evolving relationship between core collapse discoveries and that cosmic star formation history in orange, along with just, hey, if you don't know anything about the relationship between core collapse supernovae and star formation rate, you might fit this green line. So what this is basically saying is both core collapse supernovae trace in some way this rate, and this one here is theoretical on the right. So we're saying we can do this with JWST. We can figure out whether we fall on this blue line or maybe this orange line, or something really crazy is happening on this green line, to try and figure out things like what's happening with the initial mass function at high redshift, which is tied directly to these the relationship between core collapse supernovae, so massive stars at the end of their lives, and the population of how massive those stars are at high redshift. So this is the type of thing that we are interested in doing with JWST. Yes.
Is it totally coincidental that this evolving kappa, constant kappa, seems to match the star formation rate density of the universe?
No, that's intentional. So basically, you can imagine if you're creating more stars, then you're creating more stars that can explode as core collapse supernovae. And so you would expect that when at the peak of star formation at redshift 2-ish, redshift 2-ish, you would expect there to be lots of core collapse supernovae there. And at times where there aren't lots of stars being created, you would expect fewer. But if something crazy is happening with the initial mass function, or some other mechanism that is causing core collapse supernovae than star formation rate, then you would expect some large change here at high redshift. Up to redshift 2, which is as far as we've been able to do, nothing weird happening. It seems to trace star formation as we'd expect. But there has not been the opportunity to measure this at high redshift, mostly just because of needing the depth and needing the wavelength range. Beyond redshift 2-ish, you basically are redshifted out of even Hubble's near infrared camera. So you really need James Webb.
Yeah, just like a follow-up question. That's just because you mentioned the IMF in a high redshift galaxy, because I think I'm sure you'll talk about what the most distant supernova is. I think like redshift 2-ish, right?
Talk about that.
Yeah. So maybe you don't find the supernova, but could you find evidence for like enrichment of the ISN by core collapse supernovae at like early high redshift, and say that's your argument and constraints that way?
You mean like if we didn't have any supernova discoveries?
I think I'm talking more about like the kind of composition of the spectrum, like just to argue that maybe there's certain lines you wouldn't expect that come from chemical enrichment, and then you could straighten that rather than like say, oh, I need that redshift 6.
Yes. So I actually am going to talk a little bit about that as well. But so basically we have been, small spoiler for the rest of the talk, but we've been finding that our core collapse supernovae in high redshift tend to seem to have a lot of circumstellar interaction. And we are seeing that both in the spectrum and in the imaging. And so, it's basically only been like 6 months of this, of these types of discoveries, as I'll say. Yeah, that's basically the other half of this, as I'll show. So maybe just hold on. No, it's good. So I just was showing that this is, I actually flipped the axis in this one, but you can see redshift roughly 2, same kind of deal. That's basically been the limit up until James Webb. So let's talk a little bit about James Webb, which is really cool, as you'll see. So this is just little history of the universe, and I'm just overplotting basically what has happened with supernovae, right? So at z less than 1, we're pretty well covered. This has been the focus of ground-based supernova searches for quite a long time, and we're in the thousands per year being discovered in that regime. Even like with the upcoming Rubin Observatory, LSST, stuff like that, that's still going to be kind of Z, I mean, except in a lot of cases, but it's focused kind of Z less than 1, Z less than 1.5. With Hubble, in the last 20 years or so, we've found on order 10 to 20 in the Z1 to 2 range, out to around 2.2-ish. And then JWST has been kind of like the promise of, okay, we will be able to look for stuff that is in just the very early universe, redshifts of 10 or whatever. And that's something that is really unique to JWST. Spoiler alert, we haven't found anything in redshift 10. But even upcoming surveys like Roman that I will talk about, just because of the depth and wavelength range, it's not going to redshift 10. JWST's wavelength range of going all the way to 4 micron is really needed to do this kind of crazy redshift 10 sign. So there's a regime here that is unique to JWST. And we haven't actually quite gotten there yet, but we have very much extended this into this red regime, as I will show. The problem with JWST is that it has a very small field of view. So this is the series of up till cycle 3, this current point, the kind of largest patches of sky probed by JWST. And you can see these pretty small areas on the bottom, 10 to 1,000 square arc minutes, which in square degrees, the right side of this is about half a square degree. And so we're compared to things like all sky ground-based surveys and even Roman, where each pointing is about a quarter square degree. So it's about almost all the way, it's in here somewhere for one pointing. This is like the largest tiling that JWST has done and might do is this kind of area here at about a half a square degree. And for transient science, this is bad news because we really like to have deep, wide areas with repeated imaging in order to find things that change. And that's just not what JWST does. This, as you go to the right here, so like Cosmos, this is just one visit, right? A half a square degree, but they just go once and they tile it. Same with Primer and Seer, each of these really, except as I'll say, Jades. So that means we've had to get very creative, as I will say, basically looking for chance overlap between JWST observations. I'm going to start on this Jade side because we got lucky here. Jades was such a deep program, as you can see here. Jades reaching 30.5 magnitude in 9 filters, which is just crazy. For context, if you aren't doing a lot of observing, Hubble really maxes out in the like 28.5 range, maybe in some filters. So we're several magnitudes deeper than that here. And we got lucky because there's so much time that it could not be scheduled all at once. So basically, they did half the exposure time one year and half the exposure time the next year. So that gave us an opportunity to look for transits. So in the early days, as I said, we didn't have that nice opportunity. In the first year, there was no way to get significant repeated observations because there just hadn't been enough observations. But we still did some stuff. We compared JWST observations to HST observation in overlapping filters, of which there are only 2. So in the 2 overlapping filters, in the small regions that there was overlap, we did find a couple of supernovae, and you can see this is the transient name server. So every supernova that's discovered from the ground or in space is put on this website. And you can see over here on the right, the most viewed of all time is this: discovery of possible transient JWST near-Earth images in this STSS galaxy, and this is July 16th, and the first data data release for JWST was July 15th. So this was the first day of JWST observations, basically. This Mike Anguser is in our group at Space Telescope in collaboration with Gabe Rammer. So this was like basically manual blinking of JWST and Hubble images in these overlapping filters, looking for supernovae. We found several. But it really took JADES for this to really kick off. Because of this, we had 2 epochs spaced by a year, so that's sufficient to look for supernovae. And it was an area of 25 square arc minutes, which does not sound like a lot, but for JWST is a good chunk. This was basically 3 pointings of JWST. And it was reaching a depth of 30th magnitude, some of the deepest imaging that JWST has done. So that combination gave us a pretty unique opportunity to look for supernovae. And this was in collaboration with Jade's group, and this is Krista DeCourcy who kind of led this effort. So the way that we basically did this was the first half of Jade's observations happened in 2022. Because of the observing windows from with JWST, you can only be observed basically in November and December. So this was November 2022 and then November 2023. We basically just compare, now not just blinking back and forth, they had a whole pipeline set up. And you can see 3 cases here. 2 where there was a new supernova in 2023, and 1 where a supernova had faded in 2020, from 2022 to 2023. And you can see the redshifts here immediately are well beyond things that this was just one example of how large the galaxy projection is at low redshift. Okay, so this is redshift 0.7. You can see this is the little supernova here, and it's no longer down here. And then these 2 are redshift 2.8 and 3.8. So that was really cool to see, first of all. And I'll show you a couple plots of how substantial of a increase this was from Hubble. So this is the field, the JADES field. And these are the 5 supernovae that we would have found if we'd been looking with Hubble. So basically, these are the ones that were detected at the brightnesses that Hubble could go in the filters that Hubble has. So nice 5 ones, that's good. And then this was the full set of supernovae that were in that field. So it was about 50 or so, depending on what you call a supernova, somewhere between 50 and 70 supernovae between 2022 and 2023. Yeah, most of them were either too red or too faint to have been discovered with HST. Seen in another way, this is as a function of redshift, and that upper left corner is what Hubble has had access to in its reddest filter at its kind of survey depth. So it can go fainter than that, but at the depths that it has been used as a survey telescope for supernovae, which is kind of 26th magnitude, this is the range that it was probing. And all of these were the discoveries from JADE. So really either faint low redshift objects that would have just been missed, so could be plausibly impacting the the lower redshift rate of objects, or these guys coming all the way out to redshift 5. Nothing beyond redshift 5 at this point, but yeah, so this was our distribution. All right, so
all the redshifts are spexy.
Basically the ones with large error bars are photoz's, and the ones without are. So we have MSA for this field. So there's everything that has like a no error bar is a spexy, and anything that has these actual error bars are photoz's.
So most of those supernovae happen to occur in galaxies with no spectra.
Yes and no. Yes, for most of them, but that is JADES had spectroscopy that got redshifts for most of these, and then the rest of them that have spexies were part of our follow-up program, which I will be saying.
I was going to ask like a similar question, like in galaxies where you have a photosy, how are you sure that that star is just maybe not just like a random star in the galaxy that actually blow up?
You mean our galaxy?
Well, I mean, if there's maybe just like, is it possible to have like a random star, maybe it's fake that falls on?
You mean like between us and that galaxy?
Yeah.
Not really. We can rule out things like, I don't know, comets or something by just checking between exposures to make sure it didn't move. We can rule out most stellar, like galactic stellar activity based on both how far out of the galactic plane this is, which is far, and also, maybe in the single epoch, yes, but we have repeated imaging, is all I'm saying. And so then it's kind of obvious. And then, yeah, there could be like a dwarf galaxy between us and that galaxy, I guess that's possible. But, we have like spectra and light curves that show that they aren't. That's only true for up till about here, though, because you'll see these purple ones, which happen to all be the highest redshift, were the ones that were actually in 2022 and not there in 2023. So those plausibly, yeah, that's possible. I don't think it's the case, but it's possible, and it's hard to rule out with only a single epoch.
Follow-up programs also on JWST or using other instruments?
Yes, I will say that right now, basically. But yes, on JWST. So, well, yeah, I mean, I can actually kind of say it right now because it kind of has to be JWST because all these discoveries are, I mean, you could get to basically this population here with Hubble, but what we really want is spectroscopy. And that is really only possible with JWST at these magnitudes, even at the top of this 25th magnitude spectroscopy. And it needs to be in the near infrared because these are at high redshift. It's just not possible, right? Proposal sells itself. Yeah.
So I'm assuming you can't tell the difference between a supernova or maybe you have for those type of supernovas. But is there, with this observation, is there a model for like a fiducial amount of supernova range?
Yeah, that's actually what we're working on right now, basically. It is not, so you basically have to be able to split them into either type 1A or not type 1A. You don't have to do anything more than that. You have to be able to do that in order to do the rate estimations. Our first try at this, which is very active, seems that we either have more type 1A than we expect, or we are misclassifying Corpus as 1A. I think it's most likely that. It's all pretty uncertain. I would say we haven't seen anything super anomalous at high redshift out to, we're sensitive to redshifts. With J, it's like 8 or something. So probably more actually, probably out to like 9 or something. But in this small of an area, we weren't expecting necessarily to see. And you really need repeated imaging, like more than just one. So I will say that. Okay. All right. So now, what were we able to classify and see what we saw? So I'm going back to this plot. I'm going to start with 1As because that's actually what I do. It's the high redshift 1A science. So this was the extent of our thing, current 1As up till this point. I'm going to put a little line here at redshift 2 and talk about for a second why we really wanted to push beyond redshift 2, at 1.5 to 2. So this is that same line on a new plot. The black here is evolving dark energy, like our current kind of constraint on evolving dark energy. I'm going through a few things at a time, or like in a row. This is relative to the black line. So the black line is lambda CDM, no evolving dark energy, regular cosmology, and the shaded region is what our current kind of, dark energy could be evolving this much. The blue is what we kind of hope to find with high redshift type 1A supernovae, meaning they agree with our expectation of what we find at low redshift. They line up with standard cosmology. Dark energy either isn't evolving or it's evolving no more than we think it is at low redshift. And that's because 1As are the same everywhere. That's the blue. Nothing surprising happening. Now, the green shaded region is just a possible way in which changes in type 1A supernova progenitors, so the stellar physics as a function of redshift, this is metallicity, could be changing 1A brightnesses. Plausible. We don't know whether they are, but it could happen. So the red points here are what would happen if Type Ia supernovae are just systematically a little bit brighter at high redshift because of a lower metallicity, just theoretically. But you can imagine lots of things that change in redshift in progenitors. This is what they would look like. They would just be kind of systematically brighter. Now, if you made the same measurement as a function of redshift out to redshift 2 or so, you would see that you could end up thinking that this is just evolving dark energy. You know, they're systematically brighter, but the impact is lower at low redshift. And so you could be tricked into thinking, oh yeah, we're seeing evolving dark energy with Type Ia supernovae, but in reality, it's just this change in progenitor as a function of redshift. Beyond redshift 2, for a variety of reasons that I'm happy to get into more, this really diverges. If you're seeing large changes relative to our kind of standard cosmology at high redshift, it's almost certainly due to changes in progenitor and not in changes in dark energy. And so if we can just get a pretty small sample, this is a sample of 10 at z greater than 2, then we can check this. Are 1As changing as a function of redshift? Because that would be very good to know for upcoming surveys like Rubin LSST and like Roman that are really focused on finding, measuring dark energy as a function of redshift. And yeah, I see a question on.
Yeah, Justin, forgive me. So this is cool. So is the reason for the split at high redshift that the dark energy just isn't important? It is not driving the expansion of the universe at high redshift?
That is exactly why. Yeah. So at z greater than 1.5 or so, you're in the dark matter dominated universe. So if you're seeing continued changes in 1A behavior, basically as a function of redshift, you're no longer thinking that that's due to dark energy. It's going to be because there's something intrinsic changing. And so this is one goal of this. Yes.
Is the intrinsic change, would it be in the white dwarf itself or in the environment?
It could very possibly be either, but in what we're considering here, it's mostly in the companion. But it could be either. And that's the whole point, is we basically just have no idea. Let me just show this plot real quick so that, because it's going to partially be related to that. This is our sample, but if you zoom in on this section of what we have at redshifts even above 1.5, we have photometrically classified 1As, which we use, but it's not kind of the gold standard. And then we have some gravitationally lensed type 1As, which introduce a lot of systematics, basically, to use lensed type 1As. And so really we have one, that's that little black point hiding there. Oh, I just realized I'm on the wrong. So yeah, this little black point here is our only spectroscopically classified 1A beyond redshift 1.5. So we've actually never even really found any other than this one, which I'll show you in a second, type 1A beyond 1.5 in the dark matter dominated universe. So this just has not been able to be tested in the past. These are those, so that when I show you JWST spectra, you will be happier. These are the two highest spectroscopically classified 1As in that sample. So this black point here is this spectrum on the right, both from Hubble. And these are the highest redshift 1As classified with spectra before JWST. I'm not super impressed by them, but it'll give you some context for what we'll see with JWST. Yeah.
So earlier you were showing us this 1A evolution versus dark energy scenario, and you're still using really the 1A as standardizable candles distances to test this hypothesis, right? But the rates of 1As also drop like a rock as you're going to higher redshift.
Well, we don't really know, but yes.
And it takes time to form a white dwarf. Does the rate information give you any additional constraining power on evolutionary channels?
Yeah, well, evolutionary channels, supernova evolution, not dark energy evolution. Yeah. So, right, for a little bit of context there, like Autumn said, you would expect the 1A rate to be very low at high redshift because they have to be a white dwarf. So they have to evolve all the way to a white dwarf in order to explode. But we don't have a ton of information about both 1A progenitors and what's happening in high redshift. So if we suddenly found a bunch more type 1As at high redshift than we would expect, it means that the mechanism that we kind of adopt as the normal 1A scenario is not necessarily the only way to get a 1A. And so one of the things that we're really trying to do is like, okay, does our same classification system work? If this thing looks like a 1A, but it is at redshift 8, do we still call that a 1A? You know, so this is the type of thing that we're having to talk about with JWST. Yeah, are you about to have a question?
Yeah.
Yeah.
So, I mean, so if we assume that 1As evolve the way that they seem to evolve, then couldn't you use that to classify, assuming that 1As are the way that we assume them to be, can you use them to classify between core collapse and 1As in your high redshift sample?
Oh, yeah. So the problem is that, so we can do that for anything that has multiple epochs, multiple visits, but the majority of those only have one visit, like one discovery. And so at any single phase of a supernova, if you have no information about the phase,
Sure.
then there's a lot of degeneracy. And so it's very hard to tell them apart from just one visit.
Right. But I mean, this might be just completely academic, but if you assume that the 1A count has a very, very, very low rate of redshift 4, then you can sort of say that it's a 90% chance that might be a core collapse.
Yes, so there are some priors on the rate from what we call the delay time between the amount of time it takes for a 1A to explode, but that number is also uncertain. So and we also, it's like, do you want to assume it if that's kind of what we're trying to learn about? So ideally we would get some more spectroscopically classified 1As and see, are we finding anything at a redshift that we just wouldn't expect?
If this divergence does happen, can we standardize for that as well?
Yeah, we could do it. We would need a larger sample,
Right.
for sure. But the idea of this, yes, is basically to say, hey, if we know there's something wrong as a function of redshift, then when something like Roman finds a ton, as I will show, of 1As between redshift 1.5 and 3, then you'll know already that something's wrong and you'll have the statistics to hopefully correct for it.
Would it
but-
affect much like supernovae that we've seen in high spectroscopy for like less than 1.5?
So the current 1A dark energy measurements, they use that full sample I just showed, the leverage on evolving dark energy basically comes in at redshift of 1-ish, and so it depends on the progenitor property, right? But the idea of this is that most of the things that we can imagine would be impacting this would be as a function of redshift all the way to current. So it just depends on if it's something that evolves significantly between redshift 0 and 1, or if it really is something that we don't expect to change significantly until you get to redshift 2. So it depends, but yes, it could definitely be impacting things. That shaded region, though, is the extent to which we've constrained evolving dark energy. So the impact on 1A, evolution would have to be smaller than that. Okay, I'm gonna move. So we're at the point of actually looking at some of the JWST data. So this one is it has a real name, 2023 ADSY. It's just one of those official TNS names. But if you want to search it, so this was the InJADES data, 2022 on top, 2023 on bottom. You can tell by eye that this thing is very red. These are the difference images, so the difference between 2023 and 2022, and all the filters, which I let's see mine. Okay, here we go. So this is, well, basically the names are just in micron if you just move the decimal place over. So this is about 1 micron, 1.5 micron, 2 micron, 2.7 micron, all the way up to 4.4 micron. So you can see this thing is really bright in the greater than 2.7 micron and really faint in the 1 to 2 micron. So the first thing that we said was, okay, well, let's look at our spectra. So we do have a spectrum for this. So the black here is the supernova spectrum that we got. It is a little ugly, but remember that this thing is at redshift 2.9. And you saw the JWST spectra. I don't know that this is any worse than that. So the 5 colors here are a type 2p, so the core collapse supernovae with hydrogen. a type 1c and 1b. So these are the stripped envelope supernovae. And then two type 1As. This one's normal, the ones we use for cosmology. And this one is what we call calcium rich. So you can see the difference in the calcium absorption is basically this one is broader. And these tend to have some other population changes that are interesting. So we checked all of these. By eye and by statistics, you might say, yeah, this one is maybe the best, but it's not conclusive, I would say, and that is what we said. Partially it's the signal noise, partially it is the phase that this is, which is at about 20 days after peak brightness. But statistically, this one is the preferred one, but it's not super obvious that is the case. In other words, this could plausibly. Oh yeah, let me just compare over here. So this is in comparison to this. I'm not saying it's necessarily any worse, but it could still be 3 core collapse supernovae in a trench coat, right? Like this could be like 3 weird core collapse supernovae that are just masquerading as a type 1A supernova. So it's really hard to tell from the spectrum alone. So we did turn to the light curves. Here we have actually 4 light curve epochs. So this is the follow-up that we talked about. So the first epoch here, this is the discovery from James. And then we proposed for director's discretionary time, which is basically just like an emergency proposal of, hey, we didn't know about that this would happen at the time of regular proposals. So we really want you to give us time like right now. And that's how we got both the spectrum and this imaging. So we have an additional 3 epochs from that program and in these multiple filters. And this could still be 3 core collapse supernovae trench coat, to be clear, but this is a 1A model underneath it, right? So it is quite a good fit, and take my word for it, the core collapse models are a worse fit. But this one, I will say, we're calling a likely type 1A. It's at redshift 2.9. It's extremely red, even for the whole low redshift population, but it is not outside of what we've seen before. So the interesting thing about this one is, well, we won't get any more information on it other than host information in the future, hopefully. But if it is a type 1A supernova, then it is indicating some interesting stuff. One, that high redshift supernovae are potentially, type 1A supernovae are potentially, more like this calcium-rich subclass. You can see that while the rest of this spectrum actually fits better for normal 1A, the calcium feature actually matches best from the calcium-rich 1As. And also, this one, as I said, is very red. Calcium-rich 1As tend to be quite red as well. I will come back in a few slides to how this standardizes, because I'm going to also go to Cosmos Webb, where we found another 1A, and then I will compare both of them. So this is the Cosmos Webb 1A. Cosmos Webb is only 4 filters, but you can see here, this is the supernova here. And this is its host galaxy, which is this kind of banana-shaped thing. And just for fun, this is a galaxy scale gravitational lens, just for fun. And this is the 4 difference images, again, 1, 1.5, up to 4.4 micron. This one you can see is quite blue. So kind of the opposite. And our spectrum of this one is quite good. So much better than the other one in terms of matching a normal 1A. So the black again is the observed. Here, this is a normal 1A in red. It's solid. This is a 1A. It's a redshift 2.15. And I'm just showing the Hubble spectra on the right for comparison again. Okay, so where do these fall on this block is basically what we want to know. Here, so the lower redshift one is basically right on. And this high redshift one is in agreement with large uncertainties and relatively high, but still in agreement. So, this could be indicating that things are slightly off at high redshift, not statistically, but with a larger population. So basically more needed, but no clear indication for evolution at this point. Yeah.
And so without light curve for one of the 2, how do you get the luminosity? Oh, sorry.
We have light curves for both. Yeah. I didn't show the green, but it basically looks very much like the other one except blue. I just wanted to show it's definitely 1A. from the spectrum. We have a light curve. It's 3 points versus 4. These are tough.
So you use the 3 points to kind of reconstruct the,
Yeah, we have 3 points and 6 filters. So between the wavelength information, we have very good models for 1A light curves, right? So between the wavelength information and the time evolution, it's enough. And this falls top. Okay. Oh, question online, or is that an old?
and you only need 3 to 4 epochs for this to work?
Yeah, kind of minimum 3, ideally more. But like you kind of need 3 to.
But
see.
multiple filters help.
Yeah, you definitely need multiple filters. Yeah, question online or?
Yeah, Justin. So, if you should you show the spectral lineup again? Just I'm not used to looking at these, so I don't have a sense of the uncertainties. So, like, how seriously should I take all the bumps and wiggles in the measurements?
Not very. Yeah, so from this, basically, like the major, so like we would be sure that things like this is calcium, and this like broader silicon is probably real. This is leftover H alpha from the galaxy, but it is, and it's been clipped a little bit, so just keep that in mind. But like all this stuff in the UV is noise. And probably all this is noise as well, except maybe there's some sort of broad thing here, but probably not. So mostly noise. It's a little bit better in this, right? Where you can see by the match that most of this is expected behavior.
Yeah.
So yeah, mostly noise, but yeah.
Yeah. Thanks.
How do you rule out any nuclear transients like KDE or anything else?
Oh yeah. Basically just from the first one, just from the light curve in the spectrum, it doesn't look like
Points.
No, yeah. So this one has first of all 4 points, but also its spectrum does not look like a TDE. TDEs are very blue, and this thing's super red. Yeah, it could be, but I think we have TDE people in our group. They seem to rule it out. But happy to talk about it though if you want to mess with it. Okay, so we've had a lot of questions, and we're going to be a little behind here, but that's fine. So just going to like do much less time on the core collapse because it's not what I do, but I'm going to show them, and so that we can talk about it, afterwards or during this week, and I can put you in touch with the people who actually do this. So the highlights of the core collapse are we have this Redshift 2.8 guy here that is we're saying is a type 1b, and in fact, so this is just the light curve again, it's 4 points, it's the same as Jade's comparison with type 2, which is a good fit, but you'll see from the spectrum we prefer stripped envelope, and the 1A is not a good fit, especially in the blue. So this is a nice fit to a stripped envelope light curve. I'll say why this is interesting in a second. Here's the spectrum. Type 2 is a very poor match, and that's why we don't like, even though it's a good light curve fit, it's a poor match to the spectrum. And none of these are actually great fits, but the best fit ends up being this 1C broadline, which is a kind of rare subclass of these supernovae that you can see have this extremely high photospheric velocity. In fact, this one's higher than normal. And this is weird because this is like our first opportunity to look for transients, and we found kind of a weird rare subclass of core collapse supernovae. So this could be indicating that there's more of these than we would expect at high redshift. That's interesting. And again, not exactly what I do, but this is Matt Siebert's work. You can see there's a paper of Matt Siebert, and I'm happy to put you in touch if this is something that interests you. And then we have actually this one I meant to remove when I went back and forth between computers. So I'm going to skip that one and go to this one. So this is the 3 epochs of a type 2 supernova, so the hydrogen-rich supernova, the most common supernova subtype that we know of. And this is at redshift 3.5. So this is one of our highest redshift supernovae. And you can see that this thing in rest wavelength is extremely hot and blue. We have a nice SED of this. And if you put this thing on like a temperature phase of normal type 2 supernovae, this thing looks to be very close to explosion, like within a few days of explosion. So we have this imaging going what we think is within a few days of explosion at redshift 3.5. And then we have a spectrum that we got a few weeks later. So this is the spectrum at what we think is just about 10 days after peak brightness. That seems to match a pretty normal type 2 supernova. This is broad H alpha showing hydrogen. And some of these other features are probably real in the UV. This is just like kind of poorly scaled. But this is the highest redshift spectrum of a supernova that we have, that exists. We're kind of, this is all super new, like in the last, couple months, basically. But between having the imaging that we think is only a couple days after explosion and having the spectrum, we think we can do some pretty interesting progenitor investigations with this. Okay, running out of time, but I'm just going to show the lens supernovae that we discovered as well. I'm going to go one slide on how lens supernovae works so that the rest of these make any sense at all. But basically, you have some massive object. In our case, it's going to be a cluster, but just pretend that it's a galaxy in this case. And light gets bent around it. This is gravitational lensing effect. And you end up with like multiple images of that background source. So you can see there's 2 here. And then as light gets bent around this, you get some pulsing object, or in our case, a supernova. They arrive at different times due to both the changes in geometric path length and the difference in gravitational potential of the paths. So we measure this time delay, and what this ends up doing actually is being very useful for cosmology. I'm not going to talk about it, just going to show what we found, because these are quite rare. So one of these here is a Type Ia supernova at redshift 1.8. You can see the 3 images of the supernova are here in this circle. These are super rare, and we've already found 3 with JWST. So this is basically just because of its sensitivity. This one, again, these are I'm highlighting so we can talk after or this week, but this is what the model fit to the observation looked like. It was quite good at redshift 1.8 at the time. This was the highest redshift 1A that we had found with JWST. So we were showing, yeah, it seems to look like a normal 1A. We got spectra of this as well. The cool thing about this is that this is one epoch of spectroscopy, but because of that relative time delay, you get 3 spectra of the supernova at different phases. So happy to go into this as well. And this was able to measure the Hubble constant, which was the kind of primary goal. So I suspect that the Hubble tension has come up in talks in the past. This is the early universe measurement, the Type Ia supernova measurement, and this was our measurement with the lens supernova. So we've already been able to do that with just a couple of years of JWST. So kind of in agreement with both statistically, but on the Type Ia side. And then one more highlight, which is that this was a triply imaged supernova found by Hubble back in 2016. And we found another one in the same galaxy with JWST. So this is 5 images. You can't actually see it from this far away, but the supernova is in A, B, and C, and will reappear in D in about 5 years.
We have 2 different supernovae?
Yeah, 2 different supernovae, this one in 2016, this one in 2023, in the same galaxy. So this was a high redshift supernova talk, so I'm not going to talk about lensing really, but these are just too cool to not mention. These are at lower redshift, so 1.5 to 2, so lower redshift. So I just want to show them because they're so cool that I hope someone will ask me about it after. Just really JWST, very cool for these kind of high redshift supernova studies. All right, just a couple slides on what we're doing next. So I wanted to mention Nexus because it's housed here. This is where it will roughly fall. This is some of the first like long-term cadenced deep wide JWST imaging. It actually is the only that, right? So this will be the best opportunity that we have had to look for high redshift supernovae. So everything that I've done has been kind of piecemeal. We're looking here, we're looking there. This will be excellent for transient discovery and follow-up. So in the next couple of years, you should see a much larger sample of these objects. Looking forward to Roman and Rubin for lensing, that they will become complementary. These numbers have been updated in recent years, but kind of complementary with Rubin filling in the low redshift range and Roman filling in the high redshift range. So basically the point is we should have many more of these lens supernovae in the next 5 to 10 years, but at the moment we're sitting with just a few. For the Type Ia cosmology, so we mentioned, could you make corrections for 1A evolution as a function of redshift? With Roman, probably. So this is an anticipated Hubble diagram showing same distance as a function of redshift with Roman. You can see an expectation to really fill in this 1.5 to 3 range with several years of very regular 5 to 10 day cadence imaging that is quite deep and also red enough to go to these high redshifts. So this will be pretty much the time that you'll see the first very large samples of 1As, but we will still need JWST to get the spectroscopy, the types of things that we can look at. Roman's not going to be doing that. So we'll still need JWST for spectroscopy beyond redshift 1.5 or so. All right, I think I'm at the end here. So basically just highlights of everything that we found in the last basically roughly a year or so. It's been really cool. It is still basically at the level, at the point where we're finding individual cool objects, following them up, and then trying to learn what we can. That will probably be the case all the way until Roman, other than surveys like Nexus, that will be able to actually give us samples. It's not going to happen from these kind of piecemeal things. We're finding, one supernova here, one supernova here that we follow up. It's going to take these larger surveys like Nexus, so we're very excited for that. Nevertheless, we've learned quite a lot about following these high redshift supernovae and what it takes to get detailed spectroscopy and follow-up of these more interesting objects in high redshift, which will continue to happen with JWST into the future. And we are really excited about Roman in particular for this high redshift science, where the samples will be extremely large, but we do have plans to continue kind of this Roman JWST synergy, getting spectra with JWST for things discovered with Roman on the larger area. So, happy to chat more, be here all week. Thanks.
Thank you, Justin. I want a quick one. Sorry, David. What about Euclid?
Yeah, so Euclid, there's kind of two things about Euclid that makes it very difficult to use. There's the repeated imaging with Euclid that is proprietary. So as in, you have to have inside of Euclid in order to do it. And I know that within Euclid, that imaging is being used to look for supernovae. It is quite shallow in the near infrared as well. So only going to about 24.5 in the near infrared with resolution that is, 3 to 6 times worse than JWST. So it's not great for high redshift supernova science, but we are actually in the wide area thinking of comparing it to JWST and HSC imaging basically, and it's just not deep enough really to go super far. So and wide area, there's no repeated imaging, so we can't just look for Euclid supernovae there. So it's not ideal, but we are going to try.
David?
Well, thank you for the talk. I don't work on supernovae, but I've seen over the summer there's been this very public debate in the literature about JWST solving the Hubble tension between, I think, Wendy Friedman and Adam Rees. Different. So I don't know. Again, this is coming only from I don't have any dog in this fight. I do like astronomy deep though. So as a fan of
Yeah, recorded.
Oh. Okay, well, whatever. I don't think before I talk. Anyway, I was wondering if you have any thoughts on that whole discussion.
Yeah.
Just given that you
Bit of
spoke
a minefield question. No. Yeah, so what JWST has been doing for checking, the Hubble tension is mostly on the Cepheid side. The Hubble tension discussion over the last many years has been a process of, okay, well, this could be a systematic in your supernova measurement that you have not accounted for, and then the supernova side trying to test it and up till this point, ideally show that it is not causing the tension. So the one that JWST did that you probably saw the press release on was that there was a question of maybe crowding in the Cepheid calibrated galaxies causing a bias in the Cepheid photometry. And JWST with its high resolution was able to go back, check the Cepheids that were kind of potentially crowded by neighboring stars, redo the photometry and show that it didn't resolve attention. Then there was a follow-up of actually you can resolve attention if you kind of change the sample selection. I think that's still kind of going back and forth, but I think it is, continued. JWST did that the way it was supposed to be. It's not a survey telescope, so it won't be doing things like getting light curves, new H-dot measurements with that. It's all going to be these kind of, single visit things you can check like Cepheid calibration.
My question is actually about the Hubble station as well. So the plot that you showed, you were showing the measurement that you have from the supernovae that you observed with JWST, right? And it's showing, okay, there's a huge error bar, but it's like the number for the high redshift is higher than for the local redshift using supernova local and a lower redshift. And it's very different than using the early universe to make the measurement, right? It's quite interesting that the further we get with supernovae, the higher the number we get, and the larger the distance between this and the CMB measurements, right?
So if you think of this plot, that basically I just wanted to show this plot that we were able to do with JWST, which is pretty crazy because we only had 3 light curve points again. So, but a couple things to note. There we go. So these here are same thing, time delay measurement cosmology from quasars. So just for context, that this also kind of is on this high end. But this is actually the only other lensed supernova time delay measurement for cosmology, which is actually low. But this one is core collapse, and this one is 1A. So there could possibly be a difference there. We don't use like luminosity, distance or anything. It's not like it's the same evolution thing. But there could be a difference in something else related to either the host supernova properties, or it could be the way we measure the time delays. It could be a lot of things, but just to note that there have been 2, and they're actually on both sides of this. So we kind of need more. We are going to get another H-dot measurement from this guy. Between A, B, and C, the time delay is like months. And the other cool thing, I put these because I just wanted people to ask about them. So, but the cool thing about this is that same galaxy, 7 years later. This supernova Requiem, we expect to reappear up here next year, or so, next 2 years, something like that. So we are actually planning to go back and watch this cluster and observe this supernova as it reappears here at the end of the decade. So this is just a really cool system, which is why I put it in. Yeah.
You mentioned earlier when we were trying to sort out what's a 1A, what's actually a core collapse of these redshifts, that if you saw many more 1As earlier than you expected, you would kind of have to think about, okay, are they happening in a different way?
Yeah.
Are we at the point where we have some ideas about what might make basically core collapse fake out as a 1A, or are we kind of waiting until we know if we have to do that?
Yeah, mostly that. There's just like no reason that that has come up that there would be a bunch of 1As at High-Redshift. If they were, that's kind of what I was saying to Gotham, which is like, if suddenly there were, we might just need a new class for them. That is like, they look like 1As, but there must be a different mechanism creating them, because it can't be a white dwarf that evolved in 50 million years. So if it looks like a 1A and it's at High-Redshift, then it's something else weird is going on, and we'll have to come up with why. We only have our highest redshift 1A, or possibly 3-core collapse supernova and trench coat supernova, is at 2.9. It's not high enough to be worried yet. So if we started seeing them at redshift 5 or 6 or something, that's when it would be like very surprising.
So you just mentioned we will observe like more than 100 lens supernovae cases. So I'm curious if you have, what's your plan for this lens supernovae event? Like you are plan to continue processing them one by one, or there will be some pipelines or so?
Good question. Right now this is the question. And yeah, and the Rubin number here has gone all over the place, to be honest. But I would say the current number is around is actually back to about this number, but it went up for a little bit, and it's around 10 per year of like useful ones, I would say. And so this is, I think, a reasonable distribution. Yeah, so there's kind of two major efforts on this. One on the, as you might imagine, one on the Rubin side, one on the Roman side. And yeah, the idea is very much to pipeline this. This is all galaxy scale compared to the clusters that I'm talking about. So it's much more pipelinable because they're much more simple to model. For Rubin, the difficulty is actually going to be in discovery and follow-up because there's so much data, so many false positives. It's going to be hard to find the needle in the haystack. And the Rubin, resolution and cadence is not sufficient to do all the science by itself. So you will need some follow-up from space and spectroscopy. So you need to do it in a timely manner. So that's actually where most of the effort's going is in like detection, identifying real lens supernovae and triggering follow-up. For Roman, it's much easier. The time domain survey, and there's several Roman surveys, the time domain survey, which is what these numbers are for, is just a survey that runs every 5 to 10 days. It's still being decided upon for years, a couple of years. And it has the space-based resolution to just kind of, detect these without any real issue. You'll be able to resolve the multiple images. It's deep enough to get to these high redshifts up to 3 or 4. And because it's just a cadence survey every 5 to 10 days, you'll get the light curves you need to do these time delay measurements in cosmology. So Roman, although the sample is smaller, will be a lot easier. So Rubin will take a little bit of work to make it really, really good, but it gives the opportunity to build a really cool and large sample. We just need to do a little bit on the machine. It's basically all on the machine learning detection and cleaning side, and then triggering follow-up, which we have resources for.
So I have a question about the lens supernovae time delay measurements. I think it will be quite complementary to each other with time delay measurements for lens quasars, right? I mean, in the Rubin LST era, there are numerous lens quasars where you can measure time delay. And those are persistent sources, so you can measure them over and over again. So those two methods, those two approaches, should give you the same answer.
They should.
Right.
Well, all of them should.
They're both based on the time delay method, right? And they rely on the accurate reconstruction of the lens model. So what's your perspective on the current status of the comparison between lens quasar and lens the supernovae and some future promises, like we'll be able to converge on at least with this same method but different populations.
Yeah.
You can get the same answer.
Yeah, so I mean, first of all, well, yeah, I mean this one, but we agree at least with the with the quasars. But yeah, within error certainly it's an agreement. Yeah, so these should give the same answer. They do have some different systematics, not on the lens modeling side. Well, on the lens modeling side, the supernova disappears. So you don't always have the point sources there that you need to, that is kind of obscuring your clean lensing galaxy model. So that actually helps you a little bit on one supernova side. So it could plausibly lower your systematics a little bit. Both have the same systematic related to the mass sheet degeneracy. So there's a degeneracy between the way that the lens models operate and the actual absolute mass of the lens. that can be broken by knowing something else, either about the absolute brightness of your source or about the mass of the lens. So both can use velocity dispersion measurements to break that a little bit, but supernovae can use Type Ia supernovae to do that. So there's added things. So basically, there's a couple things on the supernova side that could plausibly remove some systematics that are on the quasar side at the cost of being harder to find, harder to follow up, et cetera. So my hope is that there's a very large sample, well, there's already a larger sample, but a very large sample of quasar time delays that have small statistics, small statistical errors, and potentially larger systematic errors. And then then supernovae will ideally have slightly larger statistical errors, but smaller systematic errors. And so ideally the combination should be better than one or the other is, yeah. So I agree with that.
Cool. All right, no questions online. Okay, in that case, let's thank our speaker again.